Today's lecture, I think you will really enjoy. I am very excited about these ideas. You remember I've been saying over and over in this class how hard it is to maximize functions, maximize the likelihood functions, and that the Bayesians are ahead of us on this concept, that they've got a procedure that doesn't require maximizing your function. When we're dealing with probit models, if you did any experimentation with different things outside of what was in the problem set, you saw that, a lot of times it just won't converge, or you get caught. With mixed logits, when you use log normal distributions particularly, you can't maximize the likelihood function very easily. You got to keep tweaking it. You got to find the right starting values. Even when you think you've maximized, you don't know whether it's a local or a global maximum. And that's a problem. There's no good solution to it. You just try different values. Also, these procedures that we've used entail calculating the likelihood function, which, as you get more and more complicated models, becomes harder and harder to do. The procedures that I'm going to discuss today deal with both of those issues. You don't have to maximize anything. You're taking a mean instead, as we'll see. And when they are applicable and useful, they are applicable because they avoid having to calculate the likelihood function. You never have to calculate a likelihood function. And so you can make more and more complicated likelihood functions, and as long as you can stay within this estimation procedure, it doesn't make your estimation more difficult. I'm extremely excited about this stuff. I've been doing experiments, and it seems to work just beautifully. When you do the problem sets, you'll see it too. You get to watch the procedure occurring, and it's kind of neat seeing how it works. This stuff is not known by econometricians very much. It's not taught in undergraduate classes. Most people in the field of discrete choice analysis who were brought up in a economics department generally don't know about this stuff. So it's kind of new. I think it's important that we start this cross-fertilization going. Okay, so what I want to do today is kind of an outline, is to start out with Bayesian concepts and show exactly what's going on from a Bayesian perspective. That's where these ideas were developed. Then what is interesting is we can reinterpret the results of our analysis in purely classical terms. This is something that I think is extremely important, but is also not widely utilized, because people who are brought up in a classical tradition generally don't know these methods. People who are brought up in a Bayesian tradition who do know these methods aren't interested in interpreting them classically. So this is kind of like falling in the cracks. But what I want to show is that there is a classical interpretation to what you're doing. So you can think of what you're doing in Bayesian concepts if you want, or you can equivalently think of it in classical terms. I think one of the values of this approach is that the same results can be interpreted in either way, and so you can have fruitful conversations with any, a Bayesian or a classicist on what you're finding and how to think about it. So these are the basic ideas here, and then I want to turn to, all of it has to do with taking draws from the posterior, the Bayesian posterior distribution. So I want to talk about how to draw from the posterior. And there are two procedures that turn out to be very useful. Metropolis-Hastings and Gibbs sampling, both of which I've talked about earlier a little bit. I'm going to show how they're useful in this context. Technically, Gibbs sampling is a type of Metropolis-Hastings, but you wouldn't recognize that by looking at them. The way they're both used, they look very different, and I'm going to describe them as if they're just two different techniques, though at some deep level they're connected. And then I want to use these ideas to do what's called a hierarchical Bayes estimation of mixed logit. Okay, the point here is this is simply an estimation procedure. It's not a new model. This is another confusion that exists in the field. People think that hierarchical Bayes is a new type of model that's different from, say, probit or mixed logit. It's not. It's an estimation procedure for any behavioral model. And so I'm going to show how you can use it on mixed logit, and we can then compare with what happens when you do maximum likelihood. So hierarchical Bayes is an estimation procedure. You think of it as not competing, but as an alternative to maximum likelihood. It's not a model that is an alternative to, say, probit or mixed logit. Yeah?
Can you comment on what the adjective hierarchical means?
I'll tell you exactly what it means later. What it means, I can hint at it now, is that you've got two layers of parameters. One layer of parameters depends on the other layer of parameters. So you have a hierarchy of parameters going on. Okay. How many, did you cover Bayesian analysis at all in 240? No? That's a shame. But actually the concepts are really straightforward. They make a lot of sense. And to many people, Bayesian analysis has more intuition behind it than classical analysis. And what you want to do is try to absorb that intuition, because that'll help you when you get into the techniques and stuff. The idea from Bayesian is that we've got some parameters, theta, we're going to note theta, that we as the researcher don't know. There may be some true value out there in the real world, but we don't know it. We start our analysis, however, with some concepts of what they must be, what these parameters must be. For example, a price coefficient, we start with the idea, well, it's most likely that it's negative. You know, we're open to the possibility that maybe there's a positive price coefficient out there for some people, but it's highly unlikely. So we have these prior ideas. We can summarize those into a density on these parameters. And we call that the prior density. It's what we as the researcher start out with that reflects our beliefs about the underlying parameters. It tells us, it's a summary of, or encapsulation of what our ideas are about this, these parameters that we're interested in prior to doing any analysis. Now, you can set this as being essentially flat, by, which says, well, I don't have any idea what these parameters are. And there's a tradition for doing that, because it says, it kind of makes the Bayesian analysis closer to classical, where you're not putting any of your prior beliefs into the analysis. But you don't have to. But the idea here is you can, if you want to say, I don't know anything, make these essentially flat. So you have no idea why, if one set is more likely than another. Then what you do is you observe a sample, you observe data that reveals something, supposedly, or that it depends on these parameters. And from that, you can calculate the likelihood of the parameters given the data is the likelihood function. We're all familiar with that. Of course, here it's not logged. It's the probability of the outcomes that you observe. Okay, this is capital Y for all the outcomes that you observe in your data set as a function of the parameters that you that underlie the behavior that gives rise to that outcome. And so that gives a you can think of that as a likelihood function, just as for classical. Yeah. Yeah. And then what you get from here is a posterior distribution, which is a revision of your ideas about theta, the parameters, based on what you observe in the data. So you derive what I'm calling a K, because I don't want to use a capital pi just because it's hard to distinguish the two. There's the posterior density on your parameters, which is how your beliefs about theta must logically change after you've seen the outcome of the data that you looked at. Okay, so you start out with certain ideas, you draw a sample, and that informs you about what theta must be, or how likely it is that theta is in various levels, and that gives you you then have updated concepts of what theta must be. Now, what Bayesian analysis is based on is that you can derive this from these two very straightforwardly. In particular, the posterior distribution is equal to, by Bayes' theorem, you know, I want to do the conditioning the other way. It just makes more sense. So let's change this. This is the probability of what you observe given theta. And as classicists, what we do is interpret this as a likelihood function of theta. But it's really given theta, how likely it is that you would observe what you observe. Or stated alternatively, the posterior distribution is proportional to your prior distribution times the likelihood of your data at that value of theta. This is a proportional to thing. Because notice that the denominator here is just the integral of the numerator over all possible values of theta, and hence it's just a normalizing constant that forces this to integrate to 1, so it's a density. So another way a more succinct way to say it is the posterior distribution is proportional to the prior density times the likelihood. And notice what this means is that if you've got a flat prior, meaning you have essentially no idea before you start the analysis of what this is, then your posterior essentially becomes the likelihood function. They have the same shape. It's just a normalized likelihood function. So you should already see there's like some kind of connection between classical and Bayesian stuff here. Bayesian is talking about posteriors. Classicists talk about likelihood functions. And the two have to be pretty similar in some ways. And we'll see exactly how. Yeah?
Is the likelihood function dependent on beliefs as well as the prior?
No. It's just given your theta, what is the probability of the outcome? It's exactly the same likelihood function we've used all the time, except it's not logged.
But don't you need a function form to specify the likelihood? That's my question. Don't we need to assume normal or?
Oh yes. The behavioral model that gives rise to Y has embodied in it some assumptions about everything that translates from your parameters to behavior, including maybe distributions of things, and these are the moments of those underlying distributions or whatever. So yeah. But those are behavioral statements. Those are not statements of belief about. I guess you could think of the specification of the model as being something that you have prior beliefs on too. And there you get into moving this into the realm of non-parametric or semi-parametric stuff, and that's doable.
I guess what I'm getting at is it seems like a frequentist criticized Bayesian methodology is being based on a subjective prior. That to do maximum likelihood estimation, you have to have some subjective notion of likelihood.
Oh, yeah. I don't either. We both schools incorporate your ideas both into the specification. Both schools do that, and even given the specification, the parameters, your classicists informally incorporate it all the time. If you don't get the right answer, you respecify your model. You get a positive code. So you've got them. And what Bayesians say is that, well, let's just do it formally then, instead of informally. I don't really want to get into this issue of which school is right. I am now at the position where I like both. I like to think simultaneously in both ways. There's no reason not to. You don't have to choose one or the other. You can hold both in your head at the same time.
But as you said, if we start with a flat prior density, then we can no way translate any information from that prior density into to form the likelihood function. Right?
We're getting two things separate, mixed up here. The likelihood function is based on the specification, which you somehow come up with, and whether you're a Bayesian or a classicist, you have to do that. But given that specification, a particular value of your parameters gives rise to a particular probability of that outcome. It's just a one-to-one relation. Okay? Your prior is on those parameters. Okay? So if you have no information about your parameters, it's still true that any one value of those parameters will give you a probability that your sample occurred. And this will not necessarily be flat. In fact, it's unlikely. What we have done in classical is to maximize this. All we're doing now is multiplying that by our prior. And the two are the same when the prior is flat. So now, I mean, if this is flat, you don't have to assume that this will not necessarily be flat. It's highly unlikely it'll be flat. That's what all of our classical analysis is based on, is that it's not flat. There's a maximum somewhere. Okay. Excuse me. Okay. From a Bayesian perspective, everything that a person needs to know is or that the researcher wants to talk about would be incorporated into this posterior distribution. For example, if you want to find out how likely is it, this is a function of theta now, remember? And you get some distribution. I'm not going to give it any particular shape right now. Okay. If you want to say, well, how likely is it that theta is between two values? Then what you do is you just calculate the share of the likelihood function that's between those two. And that gives you the probability that the true value is between these two. Okay. So given this, the posterior distribution, you can calculate the probability that the true theta, given what you believe to start with and given what you observed in your data, is between two values. So you can do any kind of hypothesis testing you want. There tends to be a tradition of not thinking in terms of a point estimate within this, because why should you when you've got the whole distribution there and you want to know, it's highly unlikely that any one value you come up with is going to be exactly the right one, and so you really want to see whether it's in certain ranges. And this is kind of equivalent to confidence intervals in classical stuff. The advantage of this over anything that classicists do is that this has a precise meaning when you have a finite sample, a small sample. In that if you just observe a little bit of information, it just changes your prior a little bit. But you still have a well-defined probability function, density, that describes what your beliefs now are, given the small amount of data you've observed and your prior beliefs. And so it's all very well defined, not just asymptotically, but for small samples. Nevertheless, you can talk about estimators within a Bayesian context. And there is a fully Bayesian way to do it. One meaningful estimator is the mean of the posterior, which I'm going to label consistently as theta bar. From a Bayesian perspective, you could ask the question, given my beliefs, my now informed beliefs, my posterior, about theta, if I had to choose one theta, which one would I choose to minimize my cost of being wrong? I don't believe that one theta is going to be right, because it's unlikely that any point is going to be exactly right. But what I want to do is choose one that minimizes my cost of being wrong. Okay? And then, under that idea of thinking about one individual point, I choose one value of theta, and I want to do it to minimize the cost of being wrong, we can give an interpretation to the mean. In particular, the mean is the theta that minimizes the cost of being wrong when the cost is of the form is quadratic. That is, the difference between the true and that squared is your cost. Okay? So the further your value is from the true value, the higher your cost, and it goes up in a square. Okay? So if you think costs increase quadratically with how far you are from the true value, then your best one statement, one guess of the theta is the mean. So the mean from a Bayesian perspective has some purpose. You can interpret it that way. Also, you can calculate the mean relatively easily. Suppose you've got a posterior that you can't calculate all easily. It doesn't have a closed form. For the same reason that our likelihood function, we have to simulate sometimes to get it. One way to find out what this posterior looks like is to take draws from it. Okay? And if you take enough draws, you can see what portion of the draws fall in any particular range. So that gives you that information. Or you can take a bunch of draws and take their mean, and you get this. So that's a simulated mean for your posterior, okay, based on draws from the posterior, which you can calculate if you can't do the actual integration over the whole thing. Okay. So this is all now from a Bayesian perspective. You've got a posterior. If you want the mean, you could, in theory, integrate over your posterior. Okay, this is equal to, by definition, okay. If you can't perform this integral because it's too complicated, okay, then just like we always do with integrals in simulation, we draw from k and take the average of them all. Okay? So you can get this Bayesian estimate, the mean of the posterior, in a very simple fashion. Yeah?
So that's actually a conditional mean, right? Conditional on what?
It's conditional on the data that you observe, right. Yes. There's really no way to think about it otherwise.
In a certain sense, it makes me think of taking starting values in a regular log likelihood maximization. In a sense, your starting value is your prior. So if your prior, wouldn't the theta bar, the closeness that it is to the true, depend on your prior density and the mean of the prior?
There's two statements. The second statement is answered yes, that the cost here is going to depend on your prior density because your prior density is going to enter your posterior and hence determine the likelihood of being away from the true. Your first statement, though, about this being similar to your starting values is not true. Your starting values are just where you start here when you're trying to find the maximum. And
are you going to sort of pick the one that you hope is closest?
Yeah, and that will maybe, oh, I see, the cost of iterations. That's a way to think about it, yeah. I wouldn't advise thinking about it that way. But I see that if you think the cost of your iterations, yeah. Okay, so this is a Bayesian perspective. If you can take draws from the posterior and calculate the mean, then that is a point estimate that has a particular meaning from a Bayesian perspective. If you don't want to take that mean, you can still just take draws from the posterior and see how many fall within a range, and that gives you information. So when this posterior can be drawn from, you can do all the Bayesian analysis you want by just drawing from it, and with enough draws, you'll get the relevant statistics you're interested in. So now let's translate this to classical analysis. The link between the two is provided by the Bernstein-von Mises theorem. This has a history going back to the 19th century in various forms. It keeps getting reproved in ever more general and sometimes more succinct form. And so there's many authors that are associated with this theorem, but this is the name that's been given to it over time. The Bernstein-von Mises theorem can be thought of as having three equivalent and alternative statements. The first one is that the posterior distribution comes to look more and more like a normal distribution as your sample size rises. Okay? I'm going to write this intuitively here. Essentially what this is saying, think about, try not to get caught up in this notation, because this is a little bit intuitive, sloppy notation. But nevertheless, what you're trying to say here is that the posterior distribution for any given y in your prior has a particular shape. Okay? What this theorem says is as your sample size gets bigger and bigger, this shape essentially becomes normal. It's normal centered on its own mean, whatever that mean is, and importantly, the variance is the BHHH variance of the gradient of the likelihood function, the log likelihood function. So this is our BHHH estimator in classical terms of the variance-covariance matrix of the maximum likelihood estimator. So what this is showing is that the posterior distribution becomes normal as sample size gets bigger and bigger with the same variance as the maximum likelihood estimator, B negative 1. Or B, I'm sorry, not the negative.
It's centered in the true one or in the
This is centered on its own mean. This is extremely important, and that's a little bit why this is strange, because here you've got two things that depend on your sample. This depends on sample size, and this is the mean of this posterior. Another way to say this is, it's a little more precise, but is can be very misleading. I'm going to point out exactly how you have to think about it. Is that the difference between the parameter and its mean. Okay, so the posterior density on this becomes that. Okay, this is a more precise way to state it. Okay, but it is confusing perhaps because what we're saying here, converges in distribution, is not the sampling distribution. Remember, whenever we've used this term before, we've talked about what happens if we take, calculate the statistic with one sample, and then we retake it with a different sample, and retake it with a different sample, and each time record what the answer is, and we get a distribution of answers. Okay? Here we're not doing that. Here we're saying this is the posterior, which is a density for any given sample. It's not that we're taking multiple samples, but it's a posterior for a given sample, and all we're doing is letting that sample size get larger and larger. So this is the posterior distribution of this statistic. Okay? That becomes normal with zero, mean, and the information matrix as the inverse of the information matrix as the variance. Okay? So this is a correct statement, but you have to remember that what we're saying converges in distribution is the posterior of this, not the sampling distribution. The two are related, but not, the statement is not the same.
So we have that result as sample size grows, and we also have that the mean of theta depends on y.
Mm-hmm.
So actually, is that result, is that the limit of that
Yeah.
the mean of theta?
Essentially, if we took more and more samples, what this is saying is this will essentially become a normal distribution. Exactly. Okay, so this is the basic insight that was first seen actually in the 19th century, that a posterior distribution gets more and more to look like a normal, and importantly, a normal with the information matrix, the inverse of the information matrix, as its variance. Shocking. It's actually not so shocking, because the posterior is simply the likelihood function times the prior. As sample size gets bigger and bigger, the prior becomes irrelevant. You're adding new stuff to it all the time, and so it becomes irrelevant. So you've got a likelihood function. We already know the likelihood function has a nice shape. Yeah?
Dn is the same as the likelihood function for sample size n? Or you have the...
What?
Or you define b.
D?
b?
B.
Just about where you put b equals...
B is equal to the expectation of the log of the probability for person n, evaluated at those, divided by... So this is... Huh? What was your question then?
Dn. I just wanted you to remind me.
B divided by n?
No, Pn of theta.
Oh, this is the probability for observation n as a function of theta. It becomes an element of this. If you want to be explicit, this likelihood function is that. Okay. Another way to state the Bernstein-von Mises theorem, which actually makes sense after you've seen after the first result here, is that the difference between the mean of the posterior and the maximum of the likelihood function converges to 0 as sample size increases. Essentially, the two become one and the same. Well, now this should be no surprise, given here that the likelihood function becomes normal. That the posterior becomes normal. Since the posterior becomes normal as your sample size gets bigger and bigger, the mean and the max of a normal are one and the same. So essentially this is saying the mean of the posterior and the max of the posterior are one and the same. Well, if the max of the posterior is the same as the mean, notice that the posterior is simply got the same shape as the likelihood function times the prior. For a large enough n, as sample size gets bigger and bigger, whatever you've got as your prior becomes irrelevant. The shape of your posterior is entirely determined by the likelihood function. The prior becomes irrelevant as you get more and more observations. You see more things, whatever your prior beliefs were become irrelevant, essentially. So what this is telling you is that since the shape of the posterior is the same as the shape of the likelihood function for large enough n, the maximum of this is equal to the maximum of that, and the maximum of this is equal to the mean, because this is normal. So essentially what we've got is the mean and the max becoming one and the same asymptotically. And what this leads to is the asymptotic distribution, in the same way we've always thought about it from a classical perspective, between the mean of the posterior, taken as an estimator, and the true value, has the same asymptotic distribution as maximum likelihood. What that tells us is that maximum likelihood estimation and taking the mean of the posterior are equivalent asymptotically. Large enough sample size, you get the same sampling distribution for the two of them. Notice that this is the kind of way we're linking these two. This is a statement about the posterior distribution. It has nothing to do with sampling distributions. But since the posterior distribution is normal, we get this result. Right? So the mean and the max are the same and the prior becomes irrelevant. And since we have that result, since the mean and the max become equivalent, the same asymptotically, that tells us that the distribution of the mean is the same as the distribution of the max, the sampling distribution. So you can think of these as three alternative ways of saying the same thing, but it kind of makes sense to look at them in this way. The posterior distribution gives us information that the two mean and the max converge to each other. And if that's true, then the mean has the same sampling distribution as the max, asymptotically. So we can now treat the mean just as if it were our maximum likelihood estimator. We don't even have to think Bayesian. We just take draws from a posterior and treat the mean of that, those draws as an estimator that has the same legitimacy, same interpretation as your maximum likelihood estimator.
Well, this all sounds great, but
it is.
if we already acknowledge the fact that as n goes to infinity, prior doesn't matter, so the shape of our likelihood and the posterior should be very similar. So why bother taking the mean of the posterior? Just take the mean of the likelihood function to get our...
That's essentially what we're doing. The only thing is that a likelihood function that is what's happening here. With the one exception...
Thing about maximizing the likelihood and stuff, you know.
No, you're exactly right. The only difference is that, how to put this? The likelihood function is not a density in itself. The posterior is a density. And so a function that's not a density, you can't define the mean on. What you could do is to say that if this is flat, so it's a constant, it drops out on top and bottom, and what you do is that this is a good way to think about it actually, is that the posterior distribution is simply the normalized likelihood function that makes it into a density. And that is essentially what's happening. This becomes irrelevant, or you can treat it as a constant, so it drops out. And the posterior then becomes, and all you're doing is taking draws from the likelihood function, or draws in proportion to the likelihood function. Now, the only thing that's problematic about that is, there's two things. One, sometimes it doesn't really make sense to have a flat prior. For variances, there's reasons for wanting flat, non-flat priors, or if they're flat in the standard deviations, they're not flat in the variances, and you've got to deal with those things. So that's, whatever you've done becomes irrelevant, right? But for given sample size, it's not necessarily irrelevant. The other thing is a more technical issue, and I've been trying to work on this and without success. You need to be able, if these are constant, to prove that this integral exists. Putting a proper prior, even if it's very diffuse, but it still has a maximum and gets smaller as you go further out. It can be very, very flat, but not completely flat. So effectively it's flat, but it's not exactly flat. So this has a mean, and you can integrate it to 1. Okay? So this is a proper prior that is a density. When you multiply that times this, then you know that this is going to be a proper density. Okay, I have been working with Peter Bickel, and we've been trying to solve this, of what if this is constant, so it's not a proper density. It has no mean, and you can't integrate it. It's totally flat. What conditions do you have to put on the likelihood function then to assure that it can integrate and this normalized likelihood function becomes thing? That's a technical. From a practical point of view, what you're saying is exactly right. Technically, we haven't been able to figure out what the conditions would have to be and how to determine whether they're met. But that's why I'm wanting to go in that direction. We could forget Bayesian altogether if we could just prove that the likelihood function divided by its integral is, take draws from that, and then we don't even think Bayesian. So, and I think we will. I mean, it's just I haven't accomplished that yet. Okay, where were we? Okay, so what this tells you is we have a way to get an estimator of theta that's equivalent to maximum likelihood and is extremely simple and doesn't involve maximization. We calculate, we take draws from the posterior. Okay? We take the average of those draws, and that gives us an estimator that's equivalent to maximum likelihood. We need standard errors on that estimator, right? So we need some estimate of B. How do we do that for maximum likelihood? For maximum likelihood, at the maximizing point, you calculate this BHHH Hessian and take the inverse of it, and that gives you your standard errors. Here, we don't have to do that. Notice that the posterior has B, -1, inverse, as its variance. So when we take draws, we just calculate the variance of those draws, and that gives us B inverse. So it's simple. You take a bunch of draws, take their average, that's your estimate. You take their standard deviation, and that's your standard errors. No maximization. The only thing that's difficult is how to draw from the posterior. But I'll show you, you can always find a way to draw from the posterior. And some ways are extremely quick and efficient. Okay, so does everyone believe this? If so, we'll take a break. Procedure is to take draws from the posterior distribution, average them to get your estimate, take the standard deviation of them to get your standard errors.
Small thing, why do we need the square root of n on level 2 that converges in probability?
This is actually a stronger statement than that converges. What this says is not only does the difference become 0, but if we multiply the difference by the square root of n, so that we're kind of inflating it as we get more n, it still converges to 0. So this is a stronger statement. And it turns out that this statement is useful for relating this one to these two. Let's try to derive that last property. That is equal, by definition, to what am I doing here?
Plus and minus, right?
Yeah. This is the maximum likelihood estimator. We know that this is in distribution, right? I mean, that's our standard econ. And if this part here converges in probability to 0, that means that this converges to that distribution. So you get the last result by knowing that this difference multiplied by root n is what gives you the equivalence of them. So it's a stronger condition that just the difference converges to 0. It's the difference times root n converges to 0. This is not obvious, and this is what the Bernstein-von Mises theorem actually tells you. What we get then, we're taking draws from the posterior distribution, okay, and averaging them, and that gives us our estimator. So an interesting question becomes, let's call that estimator our simulated version of the mean. Because it's not the true mean of the posterior. We're not integrating over the whole posterior. We're just taking draws from the posterior, taking that average and treating that as our estimator of the mean. So this is an estimator of your true value. We're interested in knowing what is the distribution of this statistic, just like, for all of our statistics, maximum likelihood or whatever, we're interested in this. When we're doing all the simulation-based estimators that we were describing before, remember we showed conditions under which they're consistent. For maximum simulated likelihood, to get consistency, you had to have the number of draws in simulation rise with the sample size, and you had to, for efficiency, you had to have it rise fast enough to get rid of the bias, faster than root n. Okay. Here you get better properties of this than you get for simulated maximum likelihood and the method of simulated moments. So you have nice properties. We can rewrite this as the difference between the true mean and the true value of the parameter, and then the difference between the simulated mean and the true mean. Okay, so all I've done is added and subtracted the true mean of the posterior. Okay. This we know from the Bernstein-von Mises theorem converges in distribution to that. Okay. And this, what does this converge in distribution to? What we're doing here is taking draws from a distribution and averaging them. Okay. That, by the central limit theorem, is going to have a distribution centered on the true average and a variance equal to whatever the variance of the distribution is divided by how many draws we have. So D equals number of draws. I'm going to not call it R for reasons I'll tell you in a second. So what we get is that this converges in distribution to that, which means that our estimator, since these two things are independent, these two components here are independent, converges in distribution to normal, zero mean, 1 plus 1 over D times that. Okay. So what we get is, first of all, consistent for any mean, for any D. Okay. So this is better than what we have with maximum simulated likelihood. Maximum simulated likelihood, you only get consistency if the number of draws in your simulation rises with n. Here it's consistent for any number of draws. And you get efficiency if D rises at any rate with n. Okay? Because if this rises with n, then essentially this component drops out, and you've just got B inverse, which is the same as for maximum likelihood. So this has properties, desirable properties, occurring under less stringent conditions on the simulation than you have with simulated maximum likelihood. It has full efficiency, unlike maximum method of simulated moments, when you're not using the ideal moments. Okay? Essentially, this is equivalent to maximum method of simulated scores, which has these properties, if you have an unbiased score simulator. But as we saw, it's extremely difficult to get an unbiased score simulator. So this is as good as or better than any of the simulation-based estimators that we have already dealt with. Now, I'm calling this D as the number of draws. Oh, one last thing. For a fixed number of D, you can calculate this. It's whatever your B is, which you get as the standard, the variance of your draws, okay, your estimate of that, times 1 plus 1 over D. If you've got the 1,000 draws, then essentially you've got no extra variance associated with the simulation. But you can calculate it for whatever you want. So you get consistent for any given D, and you get a formula that you can use. Now I'm calling this D instead of R for the following reason. You're taking draws differently in the two procedures. Here you're taking draws from the posterior distribution. In the simulation methods we were talking about before, you're taking draws of the unobserved factors that affect the behavior of each person. Okay, so you're doing different kinds of drawing. So that's why I'm not calling this R, just to make sure that distinction's clear. But you've got a great estimator here. It's easy to implement. It has properties that are better than any of the things we've looked at before. Okay, so now the question becomes, how do you draw from the posterior distribution? Okay. The first thing you can do, you can always do Metropolis-Hastings. I'm going to describe that later in a particular example, and so we can review it. But as you recall, Metropolis-Hastings is a procedure where you start at a particular value, move to a new value, evaluate that new one relative to the first one, and decide whether to go to it. If you do go to it, then the next time you start there, take a movement, evaluate it relative to where you were, and either go to it or don't go to it. And you just do that repeatedly for many, many draws, and that becomes draws from whatever density you're drawing from. So you can always do Metropolis-Hastings, and I've got that described in the handout I gave you. Experience has shown that if you're just doing Metropolis-Hastings on the posterior itself, this procedure is extremely slow and usually, just from a computational point of view, much worse than maximum likelihood. Why? Because essentially, if you're taking draws by Metropolis-Hastings from the posterior distribution, each time you take a draw, you're calculating the likelihood function. Okay? For maximum likelihood, you calculate the likelihood function one time for each, if you've got k parameters, then for maximum likelihood, you do k plus 1 evaluations of the log likelihood for each iteration. So let's say you've got 9 parameters, so that's 10 each time, and you've got, say, maybe 50 iterations, which is a lot of iterations. That means you're evaluating the likelihood function 500 times. For Metropolis-Hastings, you need something like 20,000 draws to walk through this process correctly and get a set of random or sufficiently good draws from the distribution. So you're essentially doing it 10,000 times instead of, say, 500. And that's a lot worse from a computational perspective. You can do it, but it's just going to end up taking a lot more time. And so a lot of the advantages are lost because of that. You might as well do maximum likelihood with a much larger number of draws and get rid of these, the advantage of this process. So then the question becomes, is there a way we can improve on that? And the answer is unquestionably yes with Gibbs sampling. What Gibbs sampling tells us is that we can draw sequentially from subsets of these parameters and get do it repeatedly and converge towards the joint distribution. So let's say that the parameters consist of 2 subparts. Okay? So we can break our parameters into 2 parts, two groups. We can calculate the conditional distributions, or conditional posteriors, for each. So this is the posterior for the first group of parameters, given the value of the second set of parameters and the data that you've got. This is the conditional distribution, or the conditional posterior for the second set, given the first set and the data. Okay? If you can calculate these conditional posteriors, and often, as we'll see, it's quite easy to do this, then you can draw a value from this, and then take that as given and draw a value of the second set of parameters, then take that as given and draw a set from the first set, and keep going back and forth, and that eventually becomes a draw. It turns out that in many situations, drawing from the conditional posteriors can be extremely quick, such that doing this kind of process ends up being much, much faster than doing Metropolis-Hastings on the entire posterior as a whole. That's when you get the advantage of this approach. If you have conditional posteriors that are easy to draw from, as we'll see that will often be the case, then you can get draws from the posterior, joint posterior, extremely quickly, and such that it's actually faster than maximum likelihood. So not only do you have better properties, but computationally, it's quicker. The whole thing, though, depends on being able to get easy to draw from conditional posteriors. If you're left withdrawing jointly from the joint posterior using just Metropolis-Hastings, this is not a good approach. It's better just stay with maximum likelihood. Okay, so now how would we do that? As you can see, the procedure that you would want to use will depend on your model, and a drawback of this approach is that you have to think about what your conditional posterior is going to be each time you come up with a new model. Okay? There's not like a general omnibus approach that'll always work. What works well for one thing won't work well for another, etc. But you start getting in the habit of seeing the conditional posteriors easily, and you can start easily seeing patterns that arise. And so this becomes, it's kind of like if everyone grew up with as much experience on figuring out conditional posteriors as we grow up with our training in maximum likelihood, we'd be able to do this at a flash. But for anyone who hasn't done this before, it takes a while to transition into it. But it's worth the effort. Okay, so let's have a mixed logit model and show how we'd do it there. And as you'll see, it actually ends up being easier than maximum likelihood. Excuse me. So we've got our model. The utility that person N gets in period T, choice period T, from alternative I depends on parameters that are specific to that person, okay, times data relating to that person in that choice situation for that alternative, plus an error term. And what we're assuming here is that the error terms, the epsilons, are IID extreme value. Okay. And beta n, I'm going to assume for this analysis, because it makes the analysis extremely easy to see and operate. Okay. I'm going to assume that they're distributed normal with B mean in the population and W covariance in the population. So they can be have a full covariance matrix. We'll see after I talk about this how you can generalize or change it to use other distributions, but let's just keep it with that. So this is our standard mixed logit model. There's nothing different. Again, hierarchical Bayes, which is what this is going to end up being, is not a different model. It's simply a different estimation procedure. Now, if we were to take a Bayesian approach, we need to specify priors on our parameters. We have parameters B and W, right? Those are the things we don't know. So let's specify our priors. Let's say that B is distributed normal with 0 and S for S approaching infinity. Okay, so essentially S is extremely large. What that gives us is a prior on B that is just barely non-flat. And by assuming it's very, very close to flat, that means that it's not going to have effect on our final results. In fact, you can set this sufficiently high such that it won't have any effect. Okay. So what this is saying, notice that this is not a distribution. This is the distribution of the betas in the population. This is our prior beliefs about the mean of that distribution. These have different, from a classical perspective, or how you think about them is different. And then let's say that this covariance matrix, we have beliefs about what the covariance matrix is too. And we can summarize those as an inverted Wishart with parameters which I'm calling IW, with parameters VO, capital VO.
Should we know what that means?
No, I'm going to get to this in a second. The reason for this is that it's simply a matter of convenience, and it can be made to be irrelevant. And so that's why we assume it. If you've taken Bayesian stuff, I'm not going to show it. When I write my book, I'll write a section on this, but it's too tedious to go through in class. But what you can recognize is that if you have a prior on a covariance matrix that's inverted Wishart, and then observe draws from a distribution that has a particular covariance matrix, then your posterior also is inverted Wishart. That's called a conjugate prior.
Wishart somebody's last name, or is it actually an English word? Wishart is.
I don't know. An inverted Wishart, one way to think about this is an inverted Wishart is a multi-dimensional generalization of an inverted gamma, and a gamma is a generalization of a chi-squared. So it's like a generalization of a generalization. What were you saying? Okay. That's true for a normal too. If you have a prior that's normal, take a set of draws from a normal distribution and then calculate the posterior is also going to be normal. So the reason we calculate both of these is it gives us a very convenient posterior. Now, you can use the same ideas without these convenient things. It's just if you've got a normal distribution for your betas, you might as well assume this because it has no effect on your results and it makes your life extremely simple. That's what you want to do with these Bayesian things. You want to get conditional posteriors that are easy to draw from. That's what gives you the computational power. Okay. A way to think about an inverted Wishart with these parameters is that it is the covariance matrix for a set of draws. It's as if you had taken a set of draws from a normal distribution. The sample was of little VO size, and you got a covariance matrix for those draws of capital VO. So this is as if you had in some previous analysis already done some analysis and observed data, and those data that you had previously observed had this covariance matrix and that sample size. And so now we're going to add to that information. But of course, from a Bayesian perspective, you don't set your priors based on your prior analysis. You base it on your beliefs. Okay, but that's the way to think about this. Is this my beliefs are as if I had had that previous information. Okay. So now what this gives us is three sets of parameters we can think in terms of. We can have the joint posterior of beta n, b, and w. These are all things that are parameters out there in the world that we don't know. The beta for each individual person, the mean of betas in the population, and the W for each person. Okay. We have a joint distribution for all of these. Okay. And we could try to draw from this. However, if you do that, it's going to be extremely difficult. It's computationally an inelegant and slow way to do it. So instead, what we use is Gibbs sampling and determine what the conditional posteriors are for each of these. So the first thing we want is the conditional posterior for each person's betas, given that we know what the population mean is, the population covariance, and the data, including the data for that person. Okay? This we can logically determine very easily. We already know that if we know the person's beta, what is the probability of their choice? It's the logit function. The probability of that person's choices given value of beta, okay, times the value of beta given that the population statistics are this. G is normal. So G is your normal density function. Okay. So the conditional posterior on beta is the probability of that beta, given what we know the population statistics to be, times the probability of that person's data, given the beta. And this is simply logit, or a product of logits if there's a series of choices going on. Okay? There's no simulation needed here. This is a closed form, and we can easily calculate it. Okay? It's quick to calculate. So now we know what that posterior is. I should say it's proportional to this, because we've got to divide by the integral and stuff, but the proportionality is all that matters. Then we want to know what is the posterior for B if we knew the betas for all n, the covariance in the population, and the data. Okay? I should step back here. This, we have a separate posterior for each person's beta. So we have n of these conditional posteriors. This is for all n. Okay? So each person, we have a conditional posterior for that person, which is the probability of a beta for that person. Okay? That's the probability of that beta in the population times the probability that that person's choices were observed given that beta, which is just a logit formula. Okay, so now we want to say, suppose we knew each person's beta, and we knew the covariance of betas in the population, what is the probability of any particular value of the mean? Okay. This is the posterior, and as I've said before, this is distributed the same as normal. Okay. The posterior, conditional posterior for the mean of the distribution, given what you observe as each person's beta in your sample, okay, is a normal distribution centered on the mean of the betas in your sample, okay, and with a covariance equal to the true covariance, which you know, we're conditioning on the true covariance, divided by n, because that's how many people are in the sample. Essentially, we're saying here, how likely is it that given, how to put this? We observe a sample of people, each with their own betas, and we observe their betas. Okay? How likely is it that those draws were obtained, those draws of beta, were obtained from a distribution that has a particular mean b? Okay? Well, the most likely b, mean for the population, is simply the mean that you observe in your sample. Okay? Everything else, it is possible that you'd have another. It's possible that the true mean in the population is greater than the mean in your sample, and it just happened by chance that you got a mean in your sample that's lower, and so it is possible. It's also possible that the mean in the population is lower than the mean in your sample. It just happened that you drew a sample that had a slightly higher than average mean. But the most likely event is that the mean in the population is the same as in your sample. And so you get a distribution of value, you get a probability density on every possible value of b that's induced by your draws of the betas for each person. This is standard, excuse me, this is sampling at its simplest. What we've got here is we have a distribution with a known variance, w, and an unknown mean. We take draws from that distribution, we observe the value, and then ask the question, what's the probability, what's the density for any particular value of the mean of that distribution? Our best estimate is the mean in our sample, and the other ones are possible. Similarly, you can then, I'm not going to show, or this shouldn't make as much sense intuitively, but we now want the conditional mean of W, the posterior, conditional posterior of W, given the other stuff. Okay, and this is distributed inverted Wishart with let me get exactly what the numbers are. VO plus N and A where our new V is now equal to the weighted sum of your prior V plus the V that you find in your sample divided by this. Okay, where the V that you find in your sample is, we know the population mean, we know the beta for each person, so we can calculate the variance as, for each person, their value minus the population mean, sum it up over all people. So this is the variance. This is the variance against the known mean in your sample. Okay?
And small n, big N.
I'm sorry?
That's always the same sample size, right?
Yes. You're doing this now on a given sample. And essentially what you're saying is that your inverted Wishart now has as its parameter a covariance matrix, which is the average of your prior covariance matrix. Okay? That's kind of like what your original beliefs were, and the covariance matrix that you observe in your sample, okay? Where your sample is draws of beta from this distribution. So for each person, you've got their values of beta. Okay? You subtract out what you know is the mean, take the covariance of the deviations from means, and that gives you the V, the covariance in your sample. You take a weighted average of that and the prior beliefs about V to get what your new value is. Obviously, if V sub 0 is very small compared to your sample size, then you essentially are just taking the covariance in your sample. I'm sorry, here, this is what you were complaining about. This is capital N, and that's capital N. Yeah?
That is my question.
What's the other one? What multiplies
Let me write this better.
on the V star?
V star is the average of the V in your, the variance in your sample and your prior variance.
Before that, it's small v sub o.
This is small v sub o. That's essentially your sample size, implicit sample size in your prior belief. Okay? This is your sample size in your sample. So if you have your prior beliefs specified as equivalent to a very small sample, saying you essentially don't know much, then this first part becomes irrelevant.
It just looks like 20, that's why.
Does it look like 20? Oh, okay. You're right. Okay. I programmed all this up for you, so you don't have to worry about the details of getting the notation right. Also, when I do the book, then it'll be written properly there, and the references have it written properly. But the idea here is you can do the conditional distributions. If you knew what the mean and the covariance was in the population, then you can easily calculate what the probability, the posterior for any particular beta is for a given person, because it's just the probability of that beta, given what the population density is, okay, times the probability of that person's choices, given that beta. And this is not involving any simulation. It's just a simple logit formula for our model here. Suppose you observe the betas for each person and the covariance in the population, but you don't know the mean. Well, there you've got a standard situation where all you're doing is you're drawing from a distribution and you want to know what the mean is. The probability of any particular value for the mean is going to be centered, it's going to be normal, centered on the mean in your sample. That's the most likely mean, is the mean that you get in your sample. But it could be other values, and yet your sample just happened to have a different mean, okay? And the variance of that is going to be the variance you're drawing from divided by how many sample points you're drawing from. That's standard concepts. The only thing that's new here is this inverted Wishart, but this should make sense also, that essentially what you're saying is the probability of any particular covariance matrix, given that you know what the betas are in your sample and the mean is essentially based on the covariance of betas from their known mean in your sample. Now you take into your priors a little bit, but that essentially becomes irrelevant eventually. Okay? And it's not that this covariance in your population, in your sample, is the population covariance, but that's the most likely possibility, just like for the mean here. But other possibilities are likely too, have some probability, and that's what this inverted Wishart does, give you a distribution of those covariance matrices given the covariance that you observe in your sample. So each of these is easy to draw from. This, you don't have any simulation, it's just the probability of a particular beta, of their sample, of a person's choices given beta. Okay. This is drawing from a normal. We know how to do that. We've done it 1,000 times. This is drawing from an inverted Wishart, which, as you'll see when you look at the code, is very fast to do also. These are extremely fast. The only thing that takes time really is this, because you've got to do it for every single person. Okay, so now how do you do this? Those are the conditional posteriors. I want to be explicit about the steps that you take. Okay, so you start with, for each of the parameters, the mean in the population, the covariance in the population, and the value of beta for each person. You start with any values you want. I start with zeros. And you'll see this thing just marches away from 0 beautifully. So you don't have problems here with your starting values in the same way you do with maximum likelihood. If you start with the wrong starting values, you can get caught in part of the likelihood function that's poorly behaved. So you've got to change your starting values. Here, it's very insensitive to your starting values. Okay, it just takes more steps, more iterations to move towards the relevant area. Okay, so then we say, let's take these two as given and calculate what that is for each person. So for all people, we do this separately for each person. We want to draw beta n1 from k posterior for that, given the mean and variance in the population and the person's actual choices. How do we do this? We use Metropolis-Hastings. But here we're using Metropolis-Hastings, unlike on the posterior for the sample as a whole, we're doing it just for the individual person. So it's a lot quicker. And errors cancel out over people, as we'll see. So how do we do that? We calculate beta n1 is equal to the old value, the original value we had, plus something that I'm calling a jumping factor. Okay, that's how much you jump from one to the next. And your jump is determined as a draw from a normal with 0 mean and the identity matrix. So if this is a k-dimensional beta, then you draw k random normal deviates, multiply each one of them by some factor sigma. Okay? I will talk later about how to choose sigma. This is something that the researcher chooses. Your procedure will work with any positive sigma. It will work better with some than with others, and so I'll talk about that in a second. But you specify what this is. It's not a parameter. It's just a user aspect of the Metropolis-Hastings algorithm that user search gets to choose, and multiply each of those random draws by that, and that gives you a new value. So essentially, if you started here, what you're doing is saying, okay, well, I'm going to take draws from a normal distribution around that to go to some new place. Let's say that was the choice. So this is beta 0, and that's beta 1. Okay? So what I've done is now moved from my original place to a new place based on this random draw. Okay? And now I want to say, do I want to move there or do I not? Okay? So to determine whether to move to beta n1, you do that by draw a value from the normal distribution, I'm sorry, a uniform distribution between u and 1, 0 and 1. Okay? So you take a draw between 0 and 1 and evaluate mu is less than or equal to the posterior distribution at the new draw compared to the posterior at the old. So k beta n1 divided by k beta n0. Okay. And what is this equal to? This is simply the probability of that person's choices given your new draw times the probability of the person's choices given the new draw times the probability of that draw given the population parameters. So this is a normal distribution telling you how likely it is to get that draw given what you know about the population, times the probability of that person's choices given that new draw, divided by the same thing for the old draw. Okay. So you're essentially comparing the posterior at the new draw with the posterior at the old draw. If this randomly chosen number is less than this, then you keep the new one. Otherwise, you don't. If yes, keep beta 1 in. If no, discard beta 1 and label beta 01 as beta n1. I changed the ordering here. Keep n1, discard n1, and label your old one as your first one. So essentially, you choose a new point. You say, how likely? What's the value of the posterior at this new point compared to the first point? Okay, and move there or not depending on the relative likelihood. Okay, if you move there, then you repeat the process next time around, starting at that point. If you don't move there, you just stay where you were and repeat the process the next time around at the point where you were. Notice that if the new beta has a higher likelihood, that is a higher posterior, than the old one, you will always move to it. Because this is going to be greater than 1. This is a uniform between 0 and 1, so this will always be below it. So if you're moving to a higher point of the posterior, you will always move there. If you're moving to a lower point, you'll move there with a certain probability. You'll move there with the ratio of the posteriors as the probability of moving there. Okay. Okay, so now this gives you a new value of beta for that person. You do that for every single person. And notice that this might be hard to, I mean, it looks like a lot of steps and it's hard to wrap your head around the whole thing, but it's extremely easy. For one person, you take k normal deviates, calculate a new beta. That's so far you've got 2k calculations going on. Okay? Then you take one draw, that's 2k plus 1, and then you calculate the ratio of the likelihood. This is a logit divided by a logit times a normal density. Those are easy to calculate. Okay? And then you do the comparison. So you've got extremely quick calculation going on here. You don't have to do any simulation within it. You don't have to calculate any integrals. Okay? So now you've got your beta for each person. To differentiate levels, let's make those like that. Now what you've got is, you want to know what your, you want to draw B1 from the conditional posterior of B1 given the beta 1 that you got for each person, which you ended up with at the end of that step, your original covariance matrix, because you haven't changed that yet, and your data. Okay? This is a draw from a normal with B bar mean and W divided by N variance, where B bar is your average of the beta n's. So for this step, all you're doing is calculating your average of the betas. You know what W is, so you just divide it by N. And then to take draws from this, you calculate B1 is equal to B plus L eta where L is the Cholesky factor of this thing. Okay? So just like you'd always do from a normal, you take a Cholesky of the covariance matrix, multiply it by normal deviates, add the mean, and you get a draw from it. Okay? So this we've done before. There's nothing new here. And as you can see, it's extremely quick. If this has, if you've got 10 coefficients, then this is a 10 by 10 matrix. You're taking a Cholesky of a 10 by 10 matrix, and then you're just doing a few calculations here on that. The only hard part is the Cholesky factorization. And then you draw a value of the covariance matrix from its posterior, given what you know is the mean in the population, your draw of the mean, your draw of all the betas, and the data. Okay, and this is a draw from an inverted Wishart with degrees of freedom equal to whatever you set as your prior plus n. That's the kind of your sample size effectively. Sample size in your sample plus your effective sample size that's incorporated into your prior. And V star, is that what I called it before? Where V star is equal to all that stuff I said before. Essentially, it's based on, just a second, taking each person's deviation from a mean, taking the covariance of that, adding it up. Okay. So this is the weighted average of the covariance in your sample and your prior covariance, with the weights being your sample size and the implicit sample size in your prior. Okay. This is also, even though you don't know right now what an inverted Wishart is, this is as easy to do as drawing from a normal. It takes a few little steps extra, but these are extremely fast to do. So what you've done here is you've moved from a situation like maximum likelihood, where you have to do simulation to get the likelihood function for the sample as a function of your parameters B and W. You've instead moved to a situation where each step is simulation free. There's no integrals going on here. And each step is extremely fast. Yeah?
In 3 and 4, do you have the same thing that you have the if yes keep and if no?
No. Here, what we're wanting to do is always draw from the conditional posterior. Here the conditional posterior is normal and inverted Wishart, and we know how to draw effectively from those. Here the conditional posterior is nothing that we know, like normal or inverted Wishart or anything, and so when you can't find other ways to draw, you revert to Metropolis-Hastings. So this is the only one that we have to use Metropolis-Hastings for it, because it's the only one that we don't know the shape. We don't have a nice convenient shape for the conditional posterior. Here it's the product of logits times a normal, which, you know, God knows what that thing is. So you use Metropolis-Hastings when you can't do that. But notice Metropolis-Hastings here is very quick, because each time you're just calculating the logit formula for the top and bottom.
We need the beta n1s to get what the B bar is, for example, right? So I guess the first step is we do it all the way until we don't change any of the betas, the Metropolis-Hastings. So we have to get an idea of what beta n1s are for every n. To find out what B bar is.
Let me say here, repeat, let's see, 2 through 4 many times. Many times. B bar is the mean of your draws of beta for each person from step 2.
Okay, no, I was just wondering if we keep doing step 2 until like we get some convergence that we don't move anymore for every n, or do we just repeat it?
That would never occur. If you repeated step 2 over and over again without changing these, you would eventually get draws that are random draws from that person's conditional posterior. You wouldn't end up with one number. This is a distribution, and you'd end up bouncing around on it. And what this is saying is every time you get a draw, go through, use that draw to get new draws of the other stuff.
And many times is how many?
Okay, now let's talk about a few technical things. This Gibbs sampling and Metropolis-Hastings both converge for enough iterations towards 2 draws from the relevant distributions. Okay, the question is, how far do you have to go? What I've set up in your program and is used often in these things is to have a burn-in period, it's called, of 10,000 draws. So you'd cycle through 10,000 times. You, in the exercise that you'll be doing, will experiment. You can what you do is you watch these things, and you'll see them trending for a while, and then you see them just bouncing around. Well, that trending is what the burn-in period is. It's getting to the distribution. Okay, and then when it bounces around, you're there. So you can pretty well see this. There are ways to test, but you can just look at it and see it to a large extent. And you can test with other things. And then after burn-in, what is called convergence, after you've reached convergence, that is, you're on the distribution and bouncing around it, I keep 1 in 10 draws. This procedure creates serial correlation in the draws, because each draw is obtained by moving from the previous one. So there's a degree of serial correlation involved in the draws. When you take 1 out of 10, you've broken down that serial correlation quite a bit. Serial correlation is not a problem, because you take the mean of serially correlated draws is still an unbiased estimator of the true mean. So there's no problem. It's just that it's easier to think of in this way. And I keep 1,000. So what that means is I'm doing 10,000 after burn-in, 10,000 before burn-in, 10,000 altogether. You'll see that this takes, hang on just a second. For a model in which we restrict the covariance to be diagonal, which is the kind of mixed logit you've estimated before, where the coefficients are all independent, it takes about the same amount of time as maximum likelihood. However, if you allow W to be unconstrained, not diagonal. This procedure takes exactly the same amount of time. It's no harder to do this for a full covariance matrix than a diagonal one. And yet maximum likelihood takes about 4 times longer, because you've got all these extra parameters and it's harder to converge with all these extra parameters, stuff like that. So this procedure in a simple mixed logit ends up being as quick as maximum likelihood, and yet in more complex mixed logits end up being tremendously faster. Also, when you have log normal distributions, all you have to do is change, in calculating k, you exponentiate the beta to make it a log normal, and the procedure is just as fast. If you do mixed logit with log normals, it's very hard converging, and often you don't reach convergence. So this actually is a procedure that works in more situations. There's some situations it doesn't work as well in, but it often works extremely well. Yeah?
What's the cost of increasing the dimension of beta n's here?
It increases linearly, which with a full covariance matrix, if you did maximum likelihood, it would increase the time exponentially. So you get an advantage there. Yeah?
You said sigma, you get back to how do you select sigma?
Oh, yes. Thank you. There has been analysis on what the optimal value of sigma is here when you're doing the jumping. And the answer is you want to have about 1/3 accepts when you do here. You can kind of think about it as half the time you're going to be going down on the likelihood function on the posterior. And so, you're kind of starting with that. So 1/3 of the time you want to have accepts. So you can adjust sigma to get more or fewer accepts. And the program I wrote adjusts this independently, endogenously. Every time it goes through this calculation, you do this for each person. So if you're doing it for, say, 430 people, you can see how many of them got accepts and how many got rejects, and adjust sigma appropriately. So you can have an endogenous adjustment of sigma, and that's what the program does. One other thing I should say when you get to the code is that this procedure is based on the idea that you've got essentially a flat prior for the normal distribution, for the mean of the normal distribution, and this is based on the idea in my code that V0 is equal to the number of coefficients, and capital V0 is equal to the identity matrix of that size. There are technical reasons for setting it at that level. In fact, if you set it below, you end up with identification problems. But what that means is if you've got, say, 6 coefficients, you're essentially saying, I've got kind of prior information that's equivalent to 6 observations. And that, of course, washes out when you're comparing it with 450 observations or whatever we do. Okay, I know that this is complicated. It took me a long time to get into this stuff because there's so many more things to remember. But if you think about the number of times you've studied maximum likelihood and how the information gradually seeps in, if you give yourself like 1/10 of the amount of time you spent on this, you'll start loving this. And so you just got to realize this is hard just because we haven't been thinking in these terms. It actually is quite wonderful. So I really encourage you to get to the problem sets, do them, and I think you'll start finding this quite exciting. So see you next week.